Hello student, to the Foundation of Classical Electrodynamics course. Under module 4, today we have lecture number 69, where we are going to discuss the Maxwell's equations in matter. Today we have class number 69, and mainly today we are going to discuss the Maxwell's wave equation in the matter, Maxwell's equation in the matter. But before that, let me cover one important thing that we missed actually. So, that is the boundary condition of the magnetic field B. If there is interface, how the magnetic boundary condition of the magnetic field appears. So, that we are going to discuss quickly, because that we are going to use this in understanding the Maxwell's wave equation in matter later. So, we know the divergence of B is 0, which gives us that the closed surface integral of B, that is the flux, should be 0. That is the equation, that is the second equation, Maxwell's equation. So, exploiting that expression, we can figure out what is the boundary condition of B. Suppose we have a surface boundary like this, suppose this is a surface, and we have below here we have B, say perpendicular component, and this is below, and over that also we have B perpendicular, but this is above, this above. This is above. So, two sections are there, below and above, and the magnetic field, the perpendicular component of the magnetic field, I write B below and B above, and the surface current that is flowing here corresponds to K vector, and that is flowing over the surface. So, we have the surface current that is flowing. Now, if I want to calculate this integral, that is the surface integral, closed surface integral, like the Gaussian surface, we need to draw a pillbox. If I draw that here, and then this is a small area we are drawing, and below that also. So, this is basically having a cross section. So, this is the small area we are having, small surface we are having, and now the condition we are going to put here is this: closed surface integral is equal to 0, and we know the perpendicular component of B below and B above, and if I do that, so if I execute that, considering the fact that the surface of these things is say delta S, then it has to be this quantity has to be B perpendicular above, I just write B A here, then delta S, and then minus B perpendicular below, and delta S is equal to 0, because other component will not be there in the surface, because when I take the B perpendicular component, then I am just taking this one along over this, and the surface is in the same direction. So, that is why B A perpendicular dot d s, and the negative sign is because the surface and B is opposite direction. However, we have also the surface here in this side and this side. In the side surfaces, I can make this length tends to 0, so that this component will no longer alive. So, only the meaningful component we have is this perpendicular component, and they will follow this equation, and that means we have a condition that B perpendicular above is equal to B perpendicular below. That means the perpendicular component of the B is continuous. That is the outcome that we had here. Also, if I want to calculate the parallel component, because this is the condition of the perpendicular component, but B for any arbitrary direction B, if I have an arbitrary direction here, say this is the direction of B, suppose it should have a perpendicular component that I already mentioned along this direction. This should be the perpendicular component, and also one can expect, or one can have a parallel component here, which we write B parallel. So, this is the way the components are distributed. So, the parallel component is still there, and I can use another equation, which is the equation for the Ampere's law essentially, and we had this again. We have closed line integral B dot dl, that quantity is mu 0 and then I enclose. This is the amount of current I enclose. I do not put the C. So, this is the amount of current that is enclosed by this closed loop. So, that is, so let us now consider what is, I mean how to make this closed loop. Again, consider the same surface, the way we consider. So, suppose this is the surface, same surface I am considering. This is the surface, and over this surface we have now my loop, and the loop is from here to here, and then I have here and have here, and then I go the downwards which is below the loop, below the surface. So, that is given by this dotted line. Okay. So, this is the way the loop is defined. Now, the current flow, the length of this loop is, suppose from here to here is say L, small l say, and this is the way the loop is there, and the surface current is flowing. So, surface current should play a role here, the way we draw the surface current. So, I just draw it like this. Now, the B parallel component, like the way we draw here, the B parallel component should be like this. So, this is the B parallel component, and B parallel, this is above, and below also we have a B parallel component like B. Now, I integrate this. Closed line integration, and that integration means I need to integrate over this closed loop, whatever the loop I draw here, Amperian loop. So, if I draw, you can see that I have B parallel above multiplied by L minus B parallel below multiplied by L, and that should be equal to, other component will no longer be there because the direction of the loop and the direction of the B is perpendicular to each other. So, they will not going to interfere. Here also the similar thing happened actually. So, here S, the direction S and the direction B, they are perpendicular. So, these components are not there. Here we have the opposite case, the perpendicular component is no longer there because this is perpendicular to the length itself, but here only the parallel component will survive, and this will be the condition. The negative sign again because of the opposite direction, the direction is opposite for the loop in this region. So, now this quantity is equal to mu 0 I enclose, and this I enclose, mu 0 I enclose, I should write simply mu 0 the current surface current density multiplied by the L, that is all. Then we simply have B parallel above minus B parallel below is equal to mu 0 and then K. So, here we can see that in the previous case we had the perpendicular component, they are conserved for magnetic field, but here we see the parallel component is not conserved. It depends on the, if there is a surface current there, then it depends on the surface current K. If the surface current is 0, however, you can have the parallel component to be continuous again. So, what is the fate of the vector potential, that we also calculate here. So, also what we have here is A above and A below, these are continuous, the vector potential seems to be continuous. So, we can do that, this vector potential is continuous, whatever the vector potential we have in the below, that is the same vector potential we have in the above part of this interface, and that we can show by, that means the parallel component and perpendicular component both are continuous. So, we can use this expression, the divergence of A is equal to 0, that is the condition we have. For for magnetostatic, this is the condition, Coulomb gauge condition is there, that is the condition that need to be satisfied by A, and then that leads to the equation, the closed line integral A, closed surface integral A dot ds equal to 0, and similarly the way we calculate for B, we can see that the A perpendicular component of the above is equal to A perpendicular component of the below, same way. So, like the magnetic field, the vector potential is also having the same relationship with the perpendicular component of above and below, they are continuous. Well, what about the other component, that you can also figure out, that let us do in the next page. So, we know that curl of A is equal to B, that is the relation we are having. Now, if I try to find out that curl of A dot ds, suppose I am making a surface integral. So, that quantity is simply closed line integral A dot dl, and that is nothing but integral of B dot ds, and that is the magnetic flux. We had this equation several times, we know that. So, this magnetic flux calculation, so we can do so here if I make a loop like this, so this is the loop, and in this loop if I calculate, so and this length suppose delta L. So, by making delta A tends to 0, we can make this phi v vanish, and in that case what we get is simply, so what happened that if I making delta L tends to 0, because this is my choice, I can make delta L according to my choice. So, we can have phi b tends to 0. That means the flux is almost 0, or the flux will vanish. Because the surface area I can make 0. So, that basically gives me an expression like A parallel above is equal to A parallel below, exploiting the same technique that we used here, right. Only difference is that I can make this delta L tends to 0 to make this surface area 0. So, flux can be 0, and then we had simply this equation. So, so this is the two condition we get, and perpendicular and parallel component, if both are conserved, then we can say that the vector field A, the vector potential A is conserved in this interface, in this boundary. If I have an interface between two, this is a boundary between the two region, then the magnetic field in the lower and magnetic field in the upper should have the relationship like this, but the vector potential that is produced in the magnetic field is continuous. So, that information maybe we can use in our future calculations. Okay, now let us, after having that, let us now go to our main topic, that the Maxwell's equation, Maxwell's equation in matter. So, in Maxwell's equation in matter, so that means previously whatever the Maxwell's equation we discuss is mainly in the free space and then calculate the wave equation in this free space, but now we are going to deal with the Maxwell's equation in matter. In matter we have two special thing. So, we have, whenever we consider the matter, we have the bound surface charge density, which is associated with the polarization of the material. If it is a dipole, if it is a dielectric, then it is related to this polarization P, which is a dipole moment per unit volume, and that is the relation. Also, we have a bound current here if the system is magnetic, and it is related to the magnetization, and we have curl cross M is equal to JB. So, these two additional components should be there in the Maxwell's equation. So, polarization current, let me try to understand, make you understand that polarization current. So, polarization current, suppose we have a rod like this, and this is the polarization, and this is the area, small area, say perpendicular direction to the polarization, and there is a difference between the two ends. There is a difference between the bound surface charge density. So, one is positive and another one is negative and another is a positive. So, one is this side and another is that side. So, there is a difference. So, the current flow ideally, so let me write it first. So, any change in the electric polarization, any change in electric polarization, that means any change in vector P involves a flow of a flow of bound current JB, which we called this JB, actually we call the polarization current. So, here we are having a change over P over the distance, and that is if I have a surface bound charge density minus and plus, there is a difference, then it leads to the flow of current. So, I can calculate this flow of current, and that is dI is the amount of current that is flowing, that is the rate change of this bound surface charge density multiplied by the area, which is perpendicular, and that eventually leads to del P del T and then dA perpendicular, because P the polarization P is sigma. So, that we know that polarization is polarization dot n is sigma. So, that is the relation we had. Okay, I do not need to write it several times. So, that expression we use here to find out that thing. So, okay, let me write it. So, P, what I am trying to say is this: P dot n is our sigma B, that we know. Okay. So, the bound current density that we are having here, which is the polarization current that we are having Jp, that is equal to the rate of change of the polarization. This is the time rate of change of the polarization, and if I make a divergence both the side, divergence of Jp, then I can have del T and the divergence of P, and this divergence of P is the rho B, that is the bound charge density. So, this rate of change of bound charge density can leads to the divergence of Jp, that is the divergence of the polarization current that is generated due to the change of time change of P, and that is due to the the flow of bound current, that leads to basically the flow of bound current. Now, it follows that this equation is simply follow the continuity equation, that if I write it in a standard way, so divergence of Jp plus del rho b del t is equal to 0. So, the continuity equation is satisfied for the polarization current Jp. The continuity equation is satisfied for that. So, we finally what we have after doing that? So, we have the total charge density into two parts. So, total charge density rho can be divided into two parts. One is the free charge density, that is the thing we always consider, but for polarized system we also have the bound charge density rho b. So, this condition is simply rho f plus minus of divergence of p, that is my rho. Also the total current, this is for total charge, okay, this is the total charge. Total charge density. What about the total current density? The total current density J is now having three components. One is the free current density that we have. Apart from that, we have a bound current density that we derived here, that is due to the change of the polarization, rate change of the polarization. And another we already had in magnetic material, and that is for this magnetization, we called it Jm. So, it is simply Jf plus the rate of change of polarization. If there is a time dependent variation of the polarization, then we have Jb, and if we have a space variation of the magnetization, then we have Gm, and if I make a curl of that quantity, then you are going to have this current density Gm. So, I have the equation now, divergence of E is equal to rho by epsilon naught, that was our equation, but this equation is going to modify here because rho I need to write in terms of rho f and rho b, which I write minus of divergence of the polarization, and this equation now become epsilon 0 E, considering this is, and plus p, I just put this side under this divergence operator, and we have rho f. This quantity, we know that we define this quantity as our d vector, displacement vector. So, eventually we have D is equal to rho f, where my D is considered to be epsilon naught E plus P. This is the way we define the rho f. So, also the other equation, because this is the equation, these two equations we need to consider where we have the source term. So, this is the equation 1 where we had the source term rho, and equation 4 also is the equation where we had the source term. So, in principle we need to modify that well, and that equation is curl cross B is equal to mu 0 is equal to mu 0 j, that is the Ampere's law. And now we will modify that mu 0 j can be divided into 3 parts, jf plus del p del t plus curl of m. That is the 3 part we had. And also I had, let me add this, because this additional term is there in Maxwell's equation, and that is the modification by Maxwell himself, and that is this term mu 0 epsilon 0 del E del T. Let us add this term as well for the completeness. Now I rearrange. So, I have curl of B, I just divide everything with mu 0. So, mu 0, and then I put this curl this side. So, I am having minus of m, that quantity is equal to Jf, this is simply the free current density, plus I have del del T of epsilon 0 E, that is already there, plus P. Again I have here this quantity which is nothing but D. So, eventually we can write this as H, and we have our modified equation, and that equation I am writing here is the curl of H is equal to Jf plus del D del T. So, this is the equation that one should follow. So, this is a modified version of the Maxwell's equation in material, where the characteristics of the material can be entered through this value of D, which is E 0 E epsilon 0 E plus the polarization P. This is the characteristics of the material, and H is B divided by mu 0 minus the magnetization. So, the polarization and magnetization are now involved, which is strictly the property of the material, and that property when you include in the Maxwell's equation, then the equation is modified, and these two equations which is having the source term is only going to be modified, because the contribution will be in the source term, and we will have two new equation. Other two equations will remain same, that is the divergence of B equal to 0 and the curl of E is equal to del B del T. So, in today's class, so what we did is we discussed the Maxwell's equation in a material. Before that, we also calculate the boundary condition of the magnetic field B, which we did in the earlier classes, but anyway. So, that information we are going to use in the next part of the topic when we discuss about the Maxwell's wave equation in a matter. So, with that note, I would like to conclude today's class. See you in the next class, and thank you for your attention.